Practice exam, problem 14. Find the bound currents, the volume and surface currents for the triangular magnet below, where the locked-in magnetization of this magnet is simply M0K hat. Now this is an equilateral triangular magnet, and so we need to find the currents here. To do this, I have to label all the sides, and I guess I should start out just with how we define the currents. So the bound current, JB, is the divergence, not divergence, is the curl of the magnetization vector, which of course is going to be equal to 0 because this is a derivative, that's a constant magnetization vector, so that's going to be equal to 0. The other one is not 0, and this is M cross n hat, where this is the magnetization field and this is the normal vector for each one of those surfaces. So I have to figure out what the normal vector for all of these surfaces are. So I'm going to have to label all of the surfaces. So I'm going to label this surface 1 and this back surface here, surface 2. And then I'm going to label the slanted surfaces. This one is going to be surface 3 and the back one here is surface 4. And then the bottom surface we can just label surface 5. Yep. Bottom surface, I'm going to label surface 5. And so I have 5 normal vectors to find here. So just drawing them, I can start to write them down what this is. My n1 vector is going to be in the minus y hat direction, so this is just minus j hat. My n2 vector is plus j hat. My n3 vector. Now this is a equilateral triangle, so it's going to come out, so if I were to draw an equilateral triangle here, this angle here is 30 degrees, right? And so this is going to be root 3 over 2 I hat plus 1/2 k hat. And my n4 is minus root 3 over 2 I hat plus 1/2 k hat. And the n5, if I were to write this down, my n5 is minus k hat. Now, might as well go ahead and write down what all of these, all of the currents that make this up are. And so we have K1, so this is a vector, all of these are vectors, is this M0 times N1, and so I'm going to have K hat cross minus J hat. K hat cross J hat is K hat cross J hat is minus I hat, so this is going to be M0 times I hat. M0 times I hat. K2 is then going to be minus M0 times I hat. K3 is, of course, just going to be, let's see, K hat cross I hat is positive J hat. Right, so N3 is going to be root 3 over 2 M0 in the positive J hat direction. And K4 is minus root 3 over 2 M0 in the negative J hat direction. And the final, K5, is of course simply 0, because K hat cross K hat is 0. Now comes the interesting part. Now comes us, so why don't I draw these currents on to see what they are. So I get constant surface currents going this way, constant surface currents going this way along that face, and then coming back along this face here. And along these two sides here, I of course have them completing the loops. Now, the interesting part of this is of course going to be when I'm looking at this at the end, and so I'm going to end up ignoring the sides, just saying they're really far away, and I'm going to look at the magnetic field through the center of this thing. So when I sketch this, I'm going to sketch this through that, and I'm going to leave that there for now. I'm actually going to draw this on a different one, because here what I want to really get at is I've got a constant surface current here going into the board, 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 and here I've got a constant surface current coming out. And so now the other thing I'd like to do is just start drawing what the magnetic field lines for these surface currents independent of each other are, and then use superposition to add them up. Now I know around this guy, so going into the board, I'm going to have the magnetic field lines that are mostly constant. I'm going to loop around like this. You know it should look something like that. And the same with this one. So I'm going to have it go around like this, and have it go around like that, and have it go around like that. Now these are going to get slightly more oval. They start out being pretty darn straight, and as I get further away they're going to look more and more circular. But look at what happens. Here, everywhere inside, especially on here, I'm going to have equal and opposite x components, but the z component is going to be the same. And so my overall magnetic field is always going to be pointing up here along this line of symmetry, which again, because I had a symmetric system, should make sense. Here, the magnetic field from this guy is ever so slightly smaller than the magnetic field from this guy, so it's actually going to point slightly towards the tip. The overall magnetic field points slightly towards the tip. When I get outside here, I'm going to have a magnetic field that points down here, and that points kind of upward here. I'm going to have it point mostly out. Same here, when I get outside, I have a magnetic field down. I have a magnetic field mostly upward, so they combine to point out. It really gets strong whenever I look at systems, right, on this, like this guy here. So this one's weaker, this one's mostly down, so it's going to point even more sideways. And so this is kind of interesting that I slightly point towards the tip. If I do come out of the side here, I'm going to have to make a sharp turn and go off almost at a right angle to the surface here, even a little bit stronger than that, and you know, come back around. And so let's see if we can combine ideas like that into a pretty drawing. So get a blank sheet to sketch from. Let's draw something that's vaguely an equilateral triangle in the center. And I know that right in the center I'm going to have a magnetic field line that I guess probably comes in from infinity and is going to go out to infinity, and it's going to look like this. Now, if I were to take a point right here and I trace it back, remember it points slightly towards the tip, so it's going to curve away slightly like this, and then at this point it's going to take a sharp right and it's going to go off. And so I now need to continue these around, and so they have to connect at some point, so I might as well just come around like that. Let's do another one. And let's do something here, very similar. This should be mirror symmetric, right? And so we get something kind of interesting from this result, which is we have a very strong diverging, or the magnetic field is getting much weaker right at the tip of this guy. Specifically, it's saying that we're going to have a huge gradient in the strength of the magnetic field. And if you remember, whenever we had if you take a magnetic dipole, the force of magnetic dipole fields is proportional to the gradient of the magnetic field. So you're actually going to get very strong forces for magnetic dipoles right here at the tip. And so you've probably seen these. We can use these to do the level splitting because in atoms, because we get a strong gradient of the magnetic field next to these tips. And so you've seen this as the Stern-Gerlach experiment. You shoot the silver atoms, and we have a strong magnetic field here, a weak magnetic field there, and they, depending on the orientation of the spin, the orientation of the magnetic dipole, it either gets deflected up or deflected down. So there you go. That is problem 14.